Hello students, welcome back. The next topic is the limit rules. Now, I told you we're going to use three approaches for limits, and this is the second. And this one is theoretically sound, but you'll see it's a bit stupid. So we'll try not to use it very often, but as I said before, theoretically, this gives you a rock-solid foundation, so you have to go through this one way or the other, even though you don't end up using this very often. Okay, here we go. There's some limit rules, and the first limit rule is, well, the rule says the trivial limit rules. Indeed, it's trivial. Limit as x approaches to c, the constant k remains at constant k. The constant is constant because it is constant. So constant remains constant because it is constant. Oh, come on. Really. How about the next rule here? As x approaches c, x approaches c. Well, this is even worse. Double the. If x goes to c, then x goes to c. It's that simple. That's why we call those trivial limit rules. Constants stay the same. X basically becomes c. Some further rules. Addition rule. Limit of sum is sum of the limits. Coefficient rule. We can multiply coefficient before or after, doesn't matter. A little bit more generalization. Multiplication rule. Limit of product is product of the limit. You can consider this A as a limit. In that case, you can consider the coefficient rule as a special case of a multiplication rule. In any case, all those are natural. One more natural rule, the division rule. Limit of quotient is quotient of the limit, and it comes with a baggage because the denominator cannot be 0, so we have to add one more condition here. The denominator m is non-zero. Otherwise, pretty natural. A little bit more? Okay, all right. Composite rule. So the limit just goes inside any function, but not any function actually, any continuous function. But then again, give me an example of a function that is not continuous. Can you find any? Well, okay, there are some functions with some discontinuity point here and there, but those are just singular. Take those away, then nearly all the functions you can think of are all continuous. In other words, most of the time, really, maybe not 100% of the time, but most of the time, you can just slip limit inside whatever. A special case includes slipping the limit inside a square root or cubing root or any kth root, inside an exponential, or inside a trigonometric function, logarithmic function. Limit just goes in. So this rule here can give you a bit of a headache, but if you take a shortcut approach, limit just goes in, then it's not going to be too hard. All right. Trivial rule, addition rule, coefficient rule, multiplication rule, division rule, all right. Composite rule, okay, that was a hard one. Now we have a couple more. The inequality rule. G is greater than or equal to f, then the limit of g is greater than or equal to limit of f. Okay, all right. So far so good, but beware. What if I drop this inequality? Is this true? Then the answer is no, that's not true. This may be strict inequality, but the conclusion should always be semi-inequality. Graphically, we can have this kind of situation. So we have a graph of f, and then we have a graph of g, Okay, all right. And then let's consider a limit. Either to the right or from the left. You see, these two graphs touch each other. So we actually have an equality in this particular case, even though f is strictly greater than g. Wait a minute, if they touch each other, then we may have this as semi-inequality here as well, right? No, not really. If I just expunge here and then define f somewhere here, and define g somewhere here like that, or g can be here, or g can be anywhere as a matter of fact, so that we have strict inequality, well, this thing still happens because aside from this single point, infinitely many points are to the left or to the right. So following the graph from the left to the right is not affected by this single point here. So the answer, if I drop this semi-inequality and make it into strict, do we have a strict inequality? The answer is no. Always, this remains as semi-inequality. The final rule, the sandwich rule. The function f is greater than or equal to g1 and less than or equal to g2. So it's sandwiched between these two. And the upper function and lower function are both going to the same limit. Then f of x is squeezed into the same limit as well. And here is a visualization. Oh, never mind. Yeah, this kind of thing. The top and bottom, and then f is squeezed in between, and then f is going to the same limit. So x squared times sine of 1 over x is greater than or equal to negative x squared and less than or equal to positive x squared because sine is between negative and positive 1. Because of this 1 over x, we have really badly behaving and heavy oscillation, but it doesn't matter. The top and bottom squeezes this graph so that we have a limit 0 here. There are many examples, of course, but this is one of many examples. It was a nice visualization, though. I don't think we're going to use a lot of inequality rules in this course. I do have one example here, but that one is going to be an optional topic because it's an advanced exercise. But all the others, please remember all those. And they're easy to remember. The trivial rule, one by one, trivial rule, addition rule, coefficient rule, multiplication rule, division rule, and finally, composite rule. Let's see, do we have an example here? Oh my! Let's discuss this in a separate video because this is the advanced topic I told you about. This one is an optional topic. Otherwise all done. So let's say section 2 is done. I have a bit of time left, so let me take an example problem from the next section and then work it out using a limit rule. Let's see. Okay. So if I use a limit rule, how can I calculate this? Well, you can use the division rule. Limit of this fraction is fraction of the limit. So we have limit of this over limit of that. That's how we can use a limit rule. Next, we can use the addition rule. the numerator can be decomposed like this. 3x squared plus limit of 5, and then divided by limit of x squared plus limit of 3x minus limit of 2. Basically the addition rule. Well, as a matter of fact, to be a little bit more precise, I should have written like this. Okay, alright, let's do that. And then what do I do? Let's use the coefficient rule. Take the 3 out, and then take the 3 out, and then take this negative out. So what did I just use? The coefficient rule. Previously I used addition, and before that I used division rule. Okay, and then let's use the multiplication rule. This x squared is x times x, so limit of x times limit of x. Again, I can do the same thing. Limit of x times limit of x. So what did I just use? I used the multiplication rule. Before that, coefficient rule. Before that, addition rule. Before that, division rule. And then finally, let's use the trivial rule. X is going to 1, then x is going to 1. If x goes to 1, x goes to 1. Make sense? So this whole thing is just 1, and this entire thing is just 1. Same thing here, x is going to 1, so this entire thing is 1. And x is going to 1, so x is going to 1. And, oh, I forgot this multiplication by 3. And then this is constant 5. Constant stays at constant because it is constant. Constant stays at constant. So what do we have? We have a trivial computation to do. 3 plus 5 is 8, and the denominator is 2. 3 minus 2, 3 minus 3, so 8 over 0 looks like that's the answer. So we can do this limit computation like this using the limit rules. What do you think? Do you like this approach? Majority of the students do not. And that's why we're going to take another approach in section 3, and we'll discuss that. For now, well, here we go. Here's an application of the limit rules, word by word, letter by letter. But I think nobody will ever do this again. Okay, that completes section 2. In section 3, we are going to talk about a little bit more practical approach of limit. Stay tuned.